today in this video, we are gonna learn the numericals based on differentiation under integral sign. So I know that you all must be knowing about the rule of DUIS, but we'll see the numerical which is based on DUIS, where we will be applying the DUIS twice to solve the numerical. And for that, here we have a question, that is, evaluate integral 0 to infinity e raised to minus x square upon x into a minus 1 upon x plus 1 upon x e raised to minus ax dx. Now, to solve this integral by DUIS, we are gonna follow certain steps. Now, if you'll see here, then in this integration, the variable is x, whereas the a is a parameter. So, what are the steps that we are gonna follow to solve this numerical? Now, these are the 5 steps. So, in step number 1, we are gonna consider the given integral as I of alpha or I of that parameter. So, here our parameter is a, so I would say this as I of a, and we'll make it as equation number 1. And then we will apply DUIS on that equation number 1 to find di by dA. So let's start. Here I'll say I of a is equal to integration 0 to infinity e raised to minus x upon x a minus 1 upon x plus e raised to minus ax upon x dx, and this is equation number 1. Now here I'll say applying DUIS on equation number 1 with respect to a. So this will give us di by dA on the LHS, whereas on the RHS we will differentiate under the integral sign, and the differentiation will be the partial differentiation. So here I'll say integration 0 to infinity dou by dou a of the function, that is e raised to minus x upon x into a minus 1 by x plus e raised to minus ax upon x, and then dx. Now let's differentiate this with respect to a. So this e raised to minus x upon x will be treated as constant. So here I'll say 0 to infinity e raised to minus x upon x outside the differentiation. Now the differentiation of a with respect to a is 1. Differentiation of 1 by x with respect to a will be 0, because this will be treated as constant, and here we will get 1 by x outside, and the differentiation of this e raised to minus ax with respect to a will be minus of x into e raised to minus ax dx. Now here we can cancel this x term, and we will get 1 minus e raised to minus ax in the bracket. So here I'll say now di upon dA is equal to integration 0 to infinity e raised to minus x upon x 1 minus e raised to minus ax dx. And guys, I'll say it as equation number 2. So if you'll see our step number 2, then it was that we have to apply the DUIS on equation number 1 and find the value of di by d alpha, that is di by dA in our case. Now if you'll see here, we have integrated by using, now if you'll see here, then we have applied the rule of DUIS on equation number 1, but we did not get the value of di by dA, because here still we have to evaluate this integral. Now the question is how to evaluate this integral, because here we have the x term in the denominator as well as we have a parameter in the question. So guys, what we'll do is we will again apply the DUIS on this integral to evaluate it. So here I'll say again applying the DUIS on equation number 2. So applying DUIS on equation number 2 with respect to A. Now guys, here you can also solve this integral by the normal rules of integration. But since if you see here that the question or the function which is given in the integral is quite complex to get the integration, hence I am applying the DUIS back with respect to parameter A, so that we can evaluate this integral in much simpler way. So here I'll say by applying DUIS it will become d square I by dA square. So guys, carefully note this step, and on the right hand side we'll get 0 to infinity, and we'll differentiate this function with respect to A partially. So by doing that we will get e raised to minus x upon x outside, and the partial differentiation of this term with respect to A would be e raised to minus ax into x dx. Now here x and x will be cancelled, so we will get integration 0 to infinity e raised to, now here I can take this minus x outside and we will get a plus 1 in the bracket dx. And now the integration of this term is very easy. So by using the integration formula, here we will get integration of this term as e raised to minus x a plus 1 upon minus of a plus 1, and limit is from 0 to infinity. Now let's apply the limit, that is infinity. So e raised to minus infinity will give us 0, middle sign negative. Now we'll put 0, so e raised to 0 will be 1, and this term is negative, so minus and minus will become positive a plus 1. So it means we will get 1 upon a plus 1 as the value of d square I by dA square. Now after that, let's see the step number 3. So step number 3 says that we have to integrate both sides to get the value of I of alpha, that is I of A in our case, and make it equation number 2. Now guys, here we have d square I by dA square as 1 upon a plus 1, and if we want to get I of A from here, then we have to integrate twice. So I'll integrate first time, and by integrating first time we will get di upon dA. So this term d square I by dA square is reduced to di by dA by doing the first time integration, and the integration of this 1 upon a plus 1 is nothing but log of a plus 1 plus c. Now to get the value of I of A, we have to again integrate. So I'll say integrating both sides again. Here we will get I of A, and here we will get integration log of a plus 1 dA. Now let's integrate this. Now what is the integration of log term? And for this we will use the rule of Liet. So here we will consider the next term as 1, and I'll rewrite this as log of a plus 1 into 1 dA. So here I am considering this log term as u and this 1 as v. So it will give us u, that is log of a plus 1 into integration of 1 with respect to a is a minus integration derivative of this u will be 1 upon a plus 1 into integration of v is a into dA. So dA. Now here we got a log of a plus 1, and obviously here we will be getting plus c since we are integrating. Now what is the integration of a upon a plus 1 dA. And to get that, we will do the adjustment over here. So in the numerator, I will add 1 and subtract 1. So that here I'll get a plus 1 minus 1, and a plus 1 and a plus 1, we can cancel it by dividing this numerator separately with a plus 1. So here I'll say this is nothing but a plus 1, and here it is minus 1, and I'll divide separately with a plus 1 in both the terms, and then we have, let's say, dA, and this first term is as it is, that is a log of a plus 1. Now let's solve this. So a plus 1 and a plus 1 is cancelled. So here we will get a log of a plus 1 minus, in the bracket, integration of 1 is a, minus, this will give us log a plus 1. So here I'll say a minus log of a plus 1 plus c. So we will make this equation as equation number 3. Now to move further and to get the value of I of a, we have to first get the value of the constant of integration c, and then we will again integrate this term on both sides to get the value of I of a. Now how to get c? And for that we have to substitute some appropriate value of a in di by dA. So here equation number 3 as well as equation number 2 is di by dA. So in these two equations we will put appropriate value of a to get the value of c. So by observing over here, if we put a as 0, then this will become e raised to 0 as 1, 1 minus 1 0, and this whole term will become 0. So di by dA can be a finite value. So here I'll say put a equals to 0 in equation number 2 and 3. So by doing this, we will get di by dA by putting a as 0 from 2, and if we put it in 3, then we will get di by dA of 0 is equal to log of 1 plus c, and log of 1 is again 0, so we will get only c. Now the value of di by dA of 0 is also 0, so it means 0 equal to c, therefore I can say c is equal to 0. So guys, we got the value of c as 0. I'll put it over here and we will get di by dA as log of a plus 1. And now we will move ahead to get the value of I of a, and for that I'll again integrate both sides with respect to a. So here we will get I of a equals to integration of log of a plus 1 dA. Now to get the value of I of a, we have to integrate this term, and since we got the log term in the integration, here we are going to use the integration by parts, and for that I'll call this term as u, and we will create the second term which is 1, and we will call it as v. So by using the integration by parts, we can get the value of this integral. So let's start. So here first term is u, so log of a plus 1 as it is, integral of v with respect to a is a, minus integration derivative of u which is 1 upon a plus 1 into integration of v which is again a into dA plus c. Now this term as it is a log of a plus 1 minus, here we'll get a upon a plus 1 dA plus c. Now, how to solve this integral? So to solve this integral, we are gonna make the adjustment in the numerator. So in the numerator, I am gonna add 1 and subtract 1, and then we'll divide that numerator separately with a plus 1. So see here what we get. So this a log of a plus 1 as it is minus, now in the integral I'll say a plus 1 and this minus 1 over here, and we'll divide separately with a plus 1 into dA plus c. Now guys, here we can cancel this a plus 1 term and we will get a log of a plus 1. Now here we got 1 and the integration of 1 is a, so a, and this is negative sign, then minus minus plus, and the integral of 1 upon a plus 1 is log of a plus 1 plus c, and this is the value of I of a, and I'll call it as equation number 4. So guys, here I got the value of integral I of a, but still here we have the constant of integration c which we have to evaluate, and for that we will consider some appropriate value of a, and we will put that value of a in I of a in equation number 4 as well as in equation number 1. So this is the equation number 1 which has I of a. So in this equation as well as in equation number 4, we will put some value of a to get that unknown c. So guys, here if you'll observe carefully, so guys, just observe carefully the equation number 1 and tell me what should we put over here to get the finite value of I of a. So I'll tell you, let's put a equal to 0. So by doing that, here we will get e raised to 0 as 1. So we'll get 1 upon x and minus 1 upon x, both will be cancelled. And since a is 0, so this term is 0, 0 into anything 0, so we will get value of integral as 0. So let's start. Here I'll say put a equals to 0 in equation number 1 and 4. So from 1 we will get I of 0 equals to 0, and from 4 we will get I of 0 equals to, so see here a is 0, so this term is 0, this term is 0, this is 0, so log 1, and log 1 is also 0, so we will just get c. And since I of 0 is 0, we will see, and we will call it here c as 0. So here we got the value of c as 0. Now we'll put this value of c in equation number 4 to get the final value of integral. So by resubstituting this value of c as 0 here, we will get I of a as, here I can take this log a plus 1 common, so log of a plus 1 outside the bracket. From here we will get a, from here we will get plus 1 minus a, and c is 0, so this is the value of I of a, and here we have evaluated the integral by using the rule of DUIS. So friends, if you like this video and if you want to learn more concepts and numericals of engineering mathematics, and also you want the updates of engineering mathematics, then log into www.ekeeda.com and you can search my videos over there and you can learn the magic of mathematics. Thank you.